Hello and welcome to Chemistry Lesson 1.07, Accuracy versus Precision. In this lesson, we're going to talk about the definitions of accuracy and precision and what the difference is between the two. You might have used these words in everyday conversations. If someone said something that wasn't true, you could say, well, that's not accurate. Or if someone had a really good play in football, you could talk about how precise their footwork was. In fact, in terms of science, they mean very different things. We can't talk about accuracy without talking about a standard. And so I want to start off with a demonstration, or not a demonstration, but a diagram that talks about the difference between the two. So I'm going to give myself 3 archery targets here, which means I have to draw circles, and that can be challenging. So I'm going to put a bullseye in the middle, and I'm going to do 3 different targets. This is why I give you guys loaded notes. Can't even get a very good circle. So if you have shot bow and arrow before, you know that the middle of the target is the goal. That's the standard for a good shot. So if you hit the center of that target, that means that you came close to the mark. You're a good marksman. The other aspect of archery is if you shoot more than 1 arrow, maybe you shoot a flight of 3 or 4 arrows, and do they all hit close together? So let's do my first target with red. So let's say my first one, I hit here, 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 and here. And let's say for my second arrow, I hit my second flight, I hit here, 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 and here. And let's say for my third, I get 4 shots right here. For my, let's start at this end and work backwards. For this flight of arrows, I hit the bullseye right in the center all 4 times. And all of my shots were close together. So this flight of arrows would be accurate and precise. For my second flight, so working backwards, these hit they're all close together. So they're in a cluster, but they're very far away from the center of the bullseye. To be accurate, you have to hit the center. To be precise, you have to be close together. So this volley of arrows would be precise, but not accurate. Well, that takes me back to my first flight. These were all pretty close to the edge of the bullseye. So these are fairly accurate. They're close to my mark, but they're not clustered together, so these could not be considered precise. So in this case, my first volley is accurate, but not precise. And let's add a 4th target here. Number 4, we'll do these in pink. So let's say I hit here, 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 and here. These would be neither accurate nor precise. So they are not either. So let's define accuracy and precision now. Let's take advantage of this space up here. So accuracy, you cannot define accuracy without talking about a standard. And often in science, we're talking about measurements. So we're talking about the accuracy or precision of measurements. So for accuracy, we're talking about I'm going to use this word closeness. That's kind of a slang. And we're going to assume we're talking about measurements. To a known standard. So you have to have something to measure it against. And in the example of archery, our known standard is the bullseye here in the center. That generates accuracy. Precision is the, I'm going to use the word closeness again, of a set of measurements. I'm going to abbreviate MEAS to each other. So when we're measuring precision, we're measuring several different measurements, and we're going to see how close they are to one another. So hence we have precise but not accurate. Well, why does this matter? Again, we can have any one of these scenarios: precision but not accurate, accurate but not precise. And we focus more on accuracy, because if something's not accurate, it's not really data we can use. So for example, when I worked as a chemist, we had outside companies that would come in and they would do calibrations on our scales to make sure the things we were weighing correctly. If you put a 10-gram mass on a scale and it read 9 grams, then everything we were doing in the lab was going to be inaccurate. And we're really going to focus the rest of our time on accuracy and how that relates to data. Here's an example of a time when scientists did not take accuracy into account. So the next video is going to be on something called significant figures. And NASA created a satellite, but the scientists didn't take into account the accuracy of their measurements when they were engineering the satellite and actually the launch booster. And when they put it on the launch pad to put it into orbit, the rocket blew up and it blew up the satellite. And that was millions of dollars. So this really does matter. Think of it this way. If you had to create something that was very high tech, you had 2 rulers. And one ruler had marks this close together, but the next ruler had marks this close together. And you had to measure a leaf, something I can actually kind of draw, a little stem. If you were measuring the length of a leaf, and this length is a fixed amount. Pick another color here, we'll make it green. Which ruler would you want to use? Well, that's pretty obvious. You want to use the ruler that has more hash marks, because it's going to give you a more accurate reading. So this is going to be more accurate. Versus this. So if these were centimeters, let's say this is 1 centimeter, and this is 1 centimeter, and that's 1 centimeter. You could say that this is going to be about 2.5 centimeters. But if I use this ruler, we're going to see that it actually could go to 2.6 or so. Well, why don't we just buy all of the lab equipment that we have here at Columbus Grove with 3 and 4 decimals after it and make it really, really accurate? I have 2 scales here in the classroom. One scale goes to the 10th place and one goes to the 1000th place. The scales that go to the 10th place cost about $100. The scales that go to 1,000th of a place cost $350 to $400. So you pay for accuracy. You can get these kind of rulers through the Army on their, grab bag day. But if I'm going to buy this, I'm going to have to go to Flynn Corporation and spend, I don't know, $5 or $6 for a good meter stick. So the more accurate something is, usually the more the equipment costs. And when you get into a very high-tech science lab, it's not unusual for things to cost even into the millions of dollars. Well, the other thing I wanted to talk about is how do we assess accuracy? And we do something called percent error. Percent error is absolute value of a known value or standard. And let's say we're experimenting. We know that this leaf, so this would be our experimental. And we divide that by the known. So in the case of a scale, let's say I am calibrating that scale. So let's do a sample problem. If I have a standard, which is a known mass, and you can buy calibration standards, and I know that it weighs 10.0 grams. And I put it on my scale. And when I put it on the scale, it reads 9.25 grams. If I want to solve for the percent error, I'm going to take the absolute value of 10 minus 9.25. I'm going to divide that by 10. So this is going to be 0.75 divided by 10. So I'm going to get, oh, you know what? I just realized I forgot something. It's going to be 0.075. I forgot something in my formula. So let me go back and add that. I have to put it into a percent form, so I have to multiply it by 100. So when I multiply this by 100, I get 7.5%. That means that anything I set on that scale, oops, I went off page, didn't I? So I multiply that by 100 and I get 7.5%. Anything I set on that scale has the ability or possibility of being 7.5% wrong. Now, what if you're measuring something for a reaction that's going to have a thermal component to it, and if you get too much of one product, it could create a dangerous situation? That's a real possibility in a lot of lab situations. So a 7.5% error on a scale means your scale is not very accurate. Now, I could put it on the scale and I could get 9.2, 9.1, 9.2, 9.15. And I could say it's a precise scale, but I wouldn't call 7.5% error accurate. I wouldn't want that for our scales in here, and I do check them from time to time. What we're going to do in the next video, now that we understand the difference between accuracy and precision, is we're going to look at something called significant figures. Significant figures are a way of keeping track of our accuracy. If I take a measurement with this ruler and I say I have 2.60895 centimeters, is that possible? It's not. I could maybe do 2.5, maybe I could do 3, I could round to a half place, but there is no way in the world I could say that I have 2.6895 centimeters with this. But yet that's what we do often in science, is we just start throwing numbers after a decimal, not really paying attention to, is this viable? Could I actually take this measurement? So the next video on significant figures will address how we keep track of our accuracy and the rules that apply to that. So your takeaways today should be, do you understand the definition of accuracy and precision? Can you describe situations that are precise but not accurate, accurate and precise, accurate, not accurate or precise, so on and so forth? And can you do percent error calculations? Thank you for watching and have a good day.